This is the Lagrange. Good, so welcome back. Let us continue with our quantization of the Dirac field. I have written here once again some highlights of the last lecture. This is the Lagrangian of the Dirac field, psi bar id slash minus m psi. This is the Euler-Lagrange equation, which is the equation of motion corresponding to this Lagrangian. It is the Dirac equation, id slash minus m psi equals 0. And then we go from the Lagrangian to the Hamiltonian by defining canonical conjugate momenta. Pi is given by I psi dagger. Okay, and the other canonical momentum was identically 0, and we have constraints and so on. But using this, we now want to do the canonical quantization procedure, which consists of the usual steps by replacing fundamental dynamical variables and fields by operators, and by replacing Poisson brackets by commutators between those operators, and by constructing a Hilbert space of states on which the operators are defined. So let's begin by writing down the appropriate relationships. So what we need are operators psi hat of x, pi hat of x, where pi hat is equal to I times psi dagger, using the constraint, and the Hamiltonian h hat is given by the d3x integral of the Hamiltonian density, which is obtained by Legendre transformation, where we plug in the operator fields and momenta. Then we have commutational relations, namely, instead of Poisson brackets, commutators, so psi hat with psi at different space arguments but the same time argument. That should be 0, and psi hat with pi hat with the same arguments is I times a three-dimensional delta function. And I stress again that this commutator is different from the scalar field, but now again similar to the Schrödinger field. Namely, it's a commutator between psi and psi dagger. That is a delta function. Whereas in the complex scalar field, the commutator between phi and phi dagger was 0. And here it's non-zero because psi dagger is actually the canonical momentum, and therefore the commutator must be non-zero. And finally, we have the commutator pi hat with the same arguments again, and that is 0. Now, however, there is a small subtlety which we want to be explicit about, namely this equation here has actually indices, right? Because the spinor is a spinor which is a 4-component object, so it carries a spinor that's called the index alpha, which runs from 1 to 4. And also psi dagger is an object with a spinor index beta, which also runs from 1 to 4. And then we should be explicit, how does the commutator depend on those indices alpha and beta? And what we require is, like in the Poisson bracket, Kronecker delta alpha beta here. So because literally the canonical momentum pi has an index alpha, and pi alpha is defined by the derivative of the Lagrangian with respect to psi alpha with the same index. And then automatically for each psi alpha there is a canonical momentum psi dagger alpha with the same index, and for those equal indices we require a non-zero commutator, and for different indices we require a 0 commutator because they are just independent variables. And now there is a much more interesting second subtlety, which is not so subtle after all, but which is extremely important, namely the question, should those objects here be fermions or bosons? This is a new question for us because we haven't discussed it in the semester so far. And so far we have always assumed that commutators are bosonic commutators with a minus. Okay? And we could do that here as well, go through the usual steps and see what happens. But you already know what will happen, namely we know that these spinor fields with spin 1/2, they are fermions. And so let us be careful and open-minded, and therefore let's just make here plus or minus, plus or minus, plus or minus, which means that we are open-minded and we use here either commutators or anti-commutators at this point, and we follow the usual steps for both cases until we see which case is better, or whether both cases are okay, or whether we can make a decision which case is actually to be preferred. But for the moment we simply allow both possibilities, and this means let's say commutator means that the particles will become bosons, and anti-commutator means the particles will become fermions. And at the moment we have no way to know which is better or to be preferred, but let's just follow both cases. Then the next.
طبعا هذا نفس الكلام الذي ذكرته، أنه نفس المعادلة يمكن أن تخرج الفوتونات البوزونات والفيرميونات. لماذا؟ لأنه من نفس وسط التفاعل تخرج كل هذه الجسيمات، وبما أن هذه المعادلة تصف طاقة مطرودة من التفاعل، إذن هذه المعادلة يمكن أن تحمل كل هذه الجسيمات وفقط باستخدام الكونسترين. هذا يعطينا معلومة جديدة، أن الكونسترين الذي هو مستخدم أنه باي هو دالة في المكان وليس الزمان، مشتق المكانية وليس مشتق الزمانية. هذا يعطينا بوزون وفيرميون، ليس فيرميون فقط. طيب ما هو البوزون؟ يعطينا بوزون سبين 1، والغريب أنه بوزون سبين 1 أيضا فيه بوزون سبين 0. يعني نحن نعلم أن الدبليو وزي هو سبين 0 ودبليو هو سبين 1. فلا لا 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 هذه المعادلة تعطينا سبين، تعطينا بوزون وتعطينا الفيرميون فقط بإدخال هل هو كوميوتيتر أو أنتي كوميوتيتر. وهذا أمر واضح جدا تفرضه نظرية علي يوسف، أنه من وسط التفاعل تخرج كل هذه الجسيمات. السؤال هو هل هناك جسيمات أخرى غير البوزونات والفيرميونات؟ نظرية علي يوسف تجيب، لكن حاليا أنا لا أستحضر إجابة، لكن إذا بحثت في النظرية يمكن أن تخبركم إذا كانت هناك جسيمات أخرى أم لا.
Step in our standard canonical quantization procedure is to say we work in the Heisenberg picture. And in the Heisenberg picture, the operators are time dependent and they satisfy an equation of motion. So what is the Heisenberg equation of motion for our field operator? Psi hat dot. Psi hat dot of x is equal to I times the commutator of h with psi hat with the same argument. And here there is always a commutator. There is always a commutator because that is an automatic consequence of the unitarity of time evolution in quantum mechanics. And anyway, even if that would be fermionic, the Hamiltonian always has a bosonic kind of nature, and so it always commutes with other objects. So here there is always a commutator. Okay, that is actually one of your exercises to evaluate this commutator. Let's write down what you have to evaluate. Here is a d3x integral over the Hamiltonian density, and the Hamiltonian density was essentially minus the Lagrangian, except that the time component here has dropped out. So it's minus the Lagrangian without the time component. So it's this psi hat r, then minus I di gamma I plus m psi hat. And let's say the argument here is x prime, and then everything here is evaluated at the argument x prime, comma, from the commutator psi hat at x. Okay. This is the Hamiltonian density, and the sum over I means that the index runs from 1 to 3, but not from 0 to 3, so the time component has dropped. Good. Now your task at home is to think about carefully how to evaluate this commutator in both cases where you have here plus or minus. But let's quickly see what happens. So psi with psi commutes or anti-commutes, so that doesn't do anything. But psi with psi bar, or which is equivalent to psi dagger, of course, that is, we can write it here as psi dagger gamma 0. So this gives a non-vanishing result. And so from here you get either a plus or minus, here you get another plus or minus. In the end you get, for both cases here, the same sign in the overall result from this single non-vanishing commutator. These two here give you a delta function. These two give you a three-dimensional delta function between x and x prime. So between that x and this x prime here, which is integrated over, then afterwards the integral collapses and x prime becomes x. These two operators have converged to the delta function, so the only thing that remains is this part here. This part here where the argument x prime has become x. So the result is then, with this I here in front, minus I gamma 0 times minus I gamma I di plus m psi hat. Okay, so this. All right, so if you bring now everything to the left side, then and you multiply with I gamma 0, then you see that here you get I gamma 0 times psi dot, and here you get I gamma I di. So these two again just combine to the full d slash, and therefore this is equivalent to saying I d slash with a full four-dimensional d slash minus m acting on the field operator psi hat of x is 0. Yep. Yes, okay, you figure it out at home how the i's work out, but this is I times psi dagger, and the commutator gives I times a delta function. So the commutator between psi and psi dagger alone gives just a delta function without the I. And so indeed here psi dagger with psi, that just gives the delta function. Right, but please do it at home once again and take care of all the signs and all the i's, and then you will verify that this is the Heisenberg equation of motion, and that is of course the Dirac equation. So we see that the field operator after canonical quantization, regardless fermions or bosons, satisfies the Dirac equation. Then a small corollary from this. Whenever you have the Dirac equation, regardless of quantum field theory or classical field theory, you can do the following. You can multiply with minus I d slash minus m from the left, and then you have basically a binomial formula. Minus I d slash minus m times plus I d slash minus m gives you binomial formula I d slash square plus m square. And I already told you at some other time, whenever you have something like that, d slash square of this slash operator gives you, as long as it gives you d mu gamma mu, gamma nu. So the d mu, d nu, they are symmetric in the indices because two derivatives commute. And therefore you can replace the gammas by the symmetrized combination, which is 1/2 of the anti-commutator. But 1/2 of the anti-commutator is just a metric tensor. Therefore this is the same as d mu, d nu times g mu nu, which is the D'Alembert operator. So this d slash square is equal to the D'Alembert operator. So the non-trivial gamma structure becomes just a unit matrix in spinor space. And this relationship, we have already used it for p slash, and it's also valid for tensor. Therefore this is the same as d mu, d nu times g mu nu, which is the D'Alembert operator. So this d slash square is equal to the D'Alembert operator. So the non-trivial gamma structure becomes just a unit matrix in spinor space. And this relationship, we have already used it for p slash, and it's also valid for the derivative slash and so on. So if you apply that here, then you simply derive D'Alembert plus m square acting on phi hat equals 0 as well. What is the name of this equation? Yeah, that is the Klein-Gordon equation. So normally names are not really important, but it's good to see that this is a familiar equation that was satisfied by the scalar field. So the Dirac field satisfies the Dirac equation, but it simultaneously also always satisfies the Klein-Gordon equation. And we can also make use of that. So that holds as well. Then that is the basic setup that we have to achieve, and now let us achieve it by constructing explicitly. And so we have several things that we need to satisfy. We need to satisfy the Dirac equation, the commutation relations, and the Klein-Gordon equation. And we have already solved the Klein-Gordon equation in a very general way, and so we can start with this. And so let us therefore write down, first of all, the most general solution of the Klein-Gordon equation. Because we have thought about this, and the general solution can be given in a very simple way by simply making use of this Lorentz invariant measure dp tilde. If we have that, the measure implements the Klein-Gordon equation. And then we can simply write down a very general Fourier ansatz, e to the minus ipx times a sub p plus e to the plus ipx times b dagger sub p. That is completely general. And here I say again that this is this Lorentz invariant measure d for p divided by 2 pi to the 4th power times 2 pi times delta of p square minus m square times the theta function of p0. So this is a manifestly Lorentz invariant way to write it, and because of the delta function here, in the Fourier modes we only get modes which satisfy the Klein-Gordon equation. And therefore this ansatz manifestly satisfies the Klein-Gordon equation, but it's also the most general solution. And at this point, these A and B, they are completely arbitrary Fourier components. But what can we say about them? They are operator valued, of course, because psi on the left-hand side is an operator, so they are also operators. And furthermore, the psi is of course a spinor, which has 4 components. So really what we are having here is a spinor with 4 entries, and each entry is an operator. Therefore, this A must also be something with 4 entries, and each entry is an operator. So it's a spinor valued operator, or an operator valued spinor, and here the same. So these are 4 component operators. We don't know anything yet about the different components, but anyway, it has 4 components, and each component is some operator which depends on P in an arbitrary way, and whatever we do, it will satisfy the Klein-Gordon equation. But now we turn to the next. We also need to satisfy the Dirac equation. So which subset of those solutions also satisfy the Dirac equation? Let's plug it in. Let's plug this into the Dirac equation. Zero is equal, so exclamation mark means that it should be satisfied. I d slash minus m acting on psi hat of x. Okay, and if we plug in this ansatz, then we get dp tilde. And the id slash is a derivative operator which now acts on these exponential functions. And then we get something. So first, in the first term, e to the ipx, what happens if we apply id slash onto this function, which depends on x? So we get some derivatives. The derivative with respect to x pulls down minus ip mu, right? And so it's the usual rule. I d mu becomes momentum. This rule applies here. So I d mu pulls down one factor of p. Therefore, this pulls down one factor of p slash minus m, acting on a of p times e to the minus ipx. Then in the second term, we have the b dagger and e to the I plus. So then we get the opposite sign, so we pull down minus p slash minus m, acting on b dagger times e to the plus ipx. So this is our result of applying the Dirac operator, and that should be 0. It's a Fourier integral. When is a Fourier integral 0? It is 0 if all Fourier modes are 0 individually. So that means this Fourier mode must be 0, that Fourier mode must be 0 for all p. And so that means now this is a matrix equation. P slash is a 4x4 matrix. M is the unit matrix times M. So we have a matrix times this 4-component operator if 0. This is a, let's say, a numerical equation between 4 operators. So it's like 4 linear combinations of our 4 operators have to give 0. This is this sort of equation. So hence we get p slash minus m acting on a of p, this 4-component object, must be 0 for all p, and the same we will say later about b. But let's first consider this a. What does it mean? This is a 4x4 matrix times 4 operators give 0, so it's a system of 4 equations between 4 operators with some numerical coefficients. And that means we have 4 equations, and we know that this matrix here has 2 eigenvalues 0. 2 linearly independent eigenvectors with 0 eigenvalue. And therefore we know that the 4 operators must be actually linear combinations of 2 independent operators, which are proportional to those eigenspinors with eigenvalue 0 of this. So let me write this down somehow so that you can remember it. We have 4 components, 4 algebraic numerical equations. The system of equation has the rank 2. So we have two linearly independent solutions. And we already know on the numerical level what are the two spinors which satisfy this equation. These are our u of p spinors. They satisfy this, and so we get, using that knowledge, the most general ansatz for the operators is the following. This a of p must be writable as one spinor, u of plus p and plus 1/2 times some operator a of p and plus 1/2 plus u of p minus 1/2 times a of p and minus 1/2. Okay, so this is then a 4-component spinor, a 4-component numerical. Numerical means the entries are numbers instead of operators. And this is one single operator. Without 4 components, it's just one component object. And so we write our 4-component operator as a numerical 4-component spinor times one operator times another 4-component spinor times another operator. And so we have two different operators, and we construct out of them a 4-component operator which satisfies this Dirac equation in momentum space. And so it's clearly the most general solution. And so we can write this compact as sum over S of u of p comma s times a of p comma s. So the important point is we have two operators for each p, and the two operators may be labeled by a label s plus minus 1/2, where we do not yet associate any meaning to this s plus minus 1/2, so it might mean spin, but we don't know that yet. But anyway, we have two, that is for sure. And let's just summarize again. P slash acting on this u of p comma s was m of u of p and s. And let me just say here on this blackboard, we do the same similarly for B decker. And if you do it for B decker, then of course the other Dirac equation must be satisfied with p slash plus m, and that is satisfied by the other spinors v of p. They satisfy this Dirac equation. So the B decker can be written as a linear combination of the v of p and s spinors times two operators B decker of p and s. And let me just write the final solution for the Dirac field onto the next blackboard. So using all these ingredients, we get our most general ansatz, which satisfies not only the Klein-Gordon but also the Dirac equation, is now psi hat of x is equal to d p tilde. And then instead of this a of p, we have now that sum here over s. So let's pull it out. Sum over s equal plus minus 1/2. And then we have e to the minus ipx times u of p comma s times a of p comma s, where these two are from here, and they together summed over s form this a of p from above. And then we have the analogous expression for b, e to the plus ipx times now v of p comma s and b decker of p comma s.
طيب نجد أن حاصل ضرب اليو بي اس مضروبة في اي بي اس عبارة عن نوميريكال ماتريس في 4 كومبوننت 4 كومبوننت. ما هي الكومبوننتس الفور؟ لا يمكن أن نقول أنه فضاء رباعي الأبعاد، وبعدين لدينا السبين، لا كده يكون 5 كومبوننت 5 كومبوننت. إذن لدينا السبين يعتبر 2 كومبوننت موجب نص سالب نص. الفضاء ليس 4 أبعاد أو 3 أبعاد، إنما بعدين، شيء غريب يعني. اللي حركة في بعد ولا حركة الثانية في البعد الآخر اللي هو معاكس له تماما، بالتالي تكون 4 أبعاد، 2 سبين و2 ترانسليشن على ما أظن. هذا ما أظنه. لا أظن أنه ليس لنا ليس ترانسليشن، إنما البوست في بعدين هو بوست، حيث أنه روتيشن للأبعاد ذات نفسها، ويجب أن يكون في بعدين. وهذه الأبعاد هي ليست أبعاد فضاء حقيقي، وإنما هي أبعاد في هيلبرت، لأن هذه اوبريترز تعمل في هيلبرت سبيس. في هيلبرت سبيس يتكون من 4 أبعاد، سبين 2 والبوست أيضا 2. على ما أعتقد هذه هي الأربع أبعاد 4 كومبوننت. هذا هو.
T/U equal MQ, T/V equal minus MV, C section, what was it? 2 4.
لكن البوست لا يحتوي على البي اللي هو المومنتوم. البوست يحتوي على الجي أو الام. البي يعني ترانسليشن، يعني حركة في خط مستقيم في فضاء حقيقي. ربما يكون يعنى به هذه فضاء حقيقي، ربما ذلك. لكن إذا ذكرنا فضاء حقيقي هذا يعني 4 أبعاد أو 3 أبعاد.
One probably from last time. Good. That is our ansatz that solves the Dirac equation, and it depends on some so far unknown operators A of P, S and B of P, S. So one difference to the scalar field is already interesting.
نعم وجدتها، لأنه هي صحيح هو كل هذه هي 4 أبعاد مكانية بالإضافة للبوست. كل هذه تختصر في السلاش. هذا السلاش موجود في بي سلاش، لأنه هذا السلاش عبارة عن جاما، والجاما تحتوي على 2 انترس و 2 زيرو. هذه هي الجاما، تحتوي على 2 انترس و 2 زيرو، اللي هو جاما نوت عبارة عن على انتي يعني مضاد الايدنتيتي اللي هو 0 1 ناقص 1 0. فبالتالي هذه المعادلة هي معادلة غريبة صراحة، هي معادلة غريبة، لكن تمثل في الفضاء رباعي الأبعاد، وبالتالي بما فيها فضاء في يعني 10 كومبوننت. هي 10 كومبوننت اللي هو 4 مومنتوم و6 بوست و روتيشن. لهذا نجد أن هذه المعادلة معقدة قليلا بسبب هذه الجاما ماتريس الموجودة في المعادلة. فالجاما تحاول أن تختزل هذه 10 كومبوننتس إلى 4 فقط. تختزل 10 إلى 4. فربما تختزل الأبعاد الرباعية الأبعاد إلى بعدين، وبالإضافة البوست ولا الروتيشن إلى 2 أيضا، تصبح 4 أبعاد. لهذا الأوبريتور يلعب في هيلبرت سبيس ولا يلعب في الريال سبيس. في الريال سبيس معادلة ديراك ستكون معقدة، لأنه هذا السبينر اللي هو اليو هاي تكون معقدة. اليو فيها 4 انتريس كما في الفيديو السابق الذي يتحدث عن معادلة ديراك. معادلة ديراك، نظرية توسع معادلة ديراك، نجد أن التمثيل اليو مضروبة في A كالآتي، تعطينا فيكتور من أو اليو ذاتها تعطينا، هي عبارة عن فيكتور. هذا الفيكتور يعني كولوم فيكتور. أول انتريس 0 0 لا 1 0، بعدين بي ناقص بي ام على بي زائد بي ام على ما اظن، على اي زائد ام على ما اظن. بعديها ايضا نفس الامر، ويعني فهي كومبينيشن بين البي والام ناقص وزائد. وبعد عندنا بسط المقام ثابت، عبارة عن اي زائد ام تربيع على ما اظن. والبسط عبارة عن بي ناقص ام سي او بي زائد ام سي. هذه المعادلة غريبة جدا، طبعا معادلة غريبة جدا، وانا مهتم بها جدا. لماذا؟ لانها بما انها ظهرت فيها الكتلة، فهذه المعادلة تستطيع ان تخبرنا شيئا عن الكتلة، بعد معرفة كيف يتصرف الزمن في داخل هذه المعادلة، يعني بعد إدخال حد الزمن داخل هذه المعادلة. هذه المعادلة لأنها كومبينيشنز كما قلت، فيها علامة الزائد والناقص. يعني السبب الذي جعل هذه المعادلة تختزل الكومبوننت من 10 إلى 4 هي سبب البسط الموجود الذي يقول بي ناقص ام سي وبي زائد ام سي. هذا ما يجعلها تختزل في البي 4 أبعاد، والام ايدنتيتي يعني والسي على ما أظن أيضا كم بعد سرعة الضوء. وبالتالي يعني بهذه الطريقة نستطيع أن نختزل هذه المعادلة إلى 4 أبعاد من 10 أبعاد، يعني شيء من هذا القبيل. هذا بالنسبة اليو تعتبر سبينر. نعم، اليو لا آسف اليو والفي والميو هي السبينر اللي هي البوست ولا الروتيشن. أما المعادلة كلها بما فيها البي المومنتوم تعبر عن نعم هذا صحيح، تعبر عن 10 كومبوننت، 10 أبعاد اللي هو 10 كومبوننت. يعني معادلة ديراك كلها تعبر عن 10، لكن اليو ذات نفسها السبينر يعبر عن 6 أبعاد اللي هو 3 روتيشن و3 بوست، هكذا. نعم هكذا هو التفسير. وعندما تضربهم كلها مع بعض يعطيك 4 أبعاد فقط، بسبب الجاما ماتريس يعطينا 4 أبعاد فقط. فتختزل معادلة ديراك كلها في 4 أبعاد، بالرغم من أن البي سلاش ناقص ام تعتبر البي ذات نفسها تعتبر 4 لوحدها، واليو تعتبر 6 والمفترض تكون 10، لكن بسبب أن الجاما دخلت في الموضوع فإنها تختزل كل ذلك ال4 أبعاد. وكما ذكرنا أن الجاما مرتبطة بالمكان ولا ترتبط بالزمن، مرتبطة فقط بالمكان ولا ترتبط بالزمن. وهذه المعادلة تعطينا نوميريكال فاليوز لكن في شكل ماتريس. كل هذه المعادلة البي سلاش ناقص الام مضروبة في اليو كلها، واليو دالة في اس والبي. غريبة ان اليو دالة في الاس والبي. كل هذه تعطينا ماتريس من 4 باي 4، لكن في النهاية تعطينا قيم. عند ضربها بالاي اوبريتور والبي داجر تعطينا اوبريتور، تعطينا فيكتور او تعطينا اوبريتور.
Namely, for each P, we do not have one A, but we have two A's for the two different values of S. And for each P, we also have two operators B dagger of S. So that looks like we have 2 degrees of freedom. For each momentum, we have one additional degree of freedom which can take 2 values. But to proceed in a technical way, we now need to solve our next item from the canonical quantization, which are the commutation relations. And here I claim the commutation relations are solved by the following. They are solved by the following ansatz, namely commutation relations between A's and B's. So what do we need? A of P comma S, commutator with A of P prime and S prime. So this commutation relation, and again I use the same plus minus as before, that should be 0. And the same is true for the B's. B with the same argument always. B with the same arguments also gives 0. A with B gives 0. And A with B dagger also gives 0. So A and B, they are completely independent of each other. They totally commute. But now the interesting thing, A with A dagger, that is non-zero, and that is the usual as in the case of scalar fields. Namely, we have this normalization factor, which you by now probably memorize. It's always the same, 2 pi cubed times 2p0 times a 3-dimensional delta function of p minus p prime. But now we have in addition Kronecker delta ss prime, because we have for each P we have 2 operators, and they also commute with this Kronecker delta. And similarly for B, but not identically. And now that is partly your exercise to check this, because for the B's it depends on the statistics. What you need for the B's in order that the psi and pi satisfy what they need to satisfy. What you need is B dagger with B, that is the same. So it's the same. I just copy it. That is the same. But you see, if you have bosons, and here the dagger is on the left, that is no misprint. So if you have bosons, then that means the commutator B with B dagger has a minus sign. B with B dagger, which would be the normal order, that has on the right hand side a minus sign. And however, for fermions, the order doesn't matter. For fermions, you could say B, B dagger, anti-commutator gives this result. So careful, but with this choice, it works for both fermions and bosons, and that is your task to check this. Let me just start. So in order to prove it, you first always need to fix the times of all field operators must be the same. And then we look at, for example, psi of x with psi of y plus or minus. So that would be the first commutator. Who remembers what is the supposed result of that commutator? So anti-commutator. Maybe the last row, somebody. That should be 0. So that should be 0, but okay. Now we should plug in this ansatz. We should plug in this ansatz and plug in those relationships and then check what is the result. So can you do this? 20 seconds of time. Imagine plugging that here and here, and then those commutation relations. So what is the result of this commutator? Right, so superficially that would be the structure. You have a few integrals, a few sums, and then here you have some factors times a, some plus some factors times b dagger, and here the same, with some arguments. And now you look on the left. A with a gives 0. A with b dagger gives 0. B dagger with b dagger gives 0. So that means overall, whatever you look at, all terms give 0. So therefore, this is 0. That is the easy part. The more complicated part would be psi with psi dagger. Psi with psi dagger. And that is really a calculation. Plus minus, and maybe let us start. So what you would write down, dp tilde prime, okay, then sum over s prime. Then we have here in the commutator from the left we have exactly this expression here. So we have e to the minus I px u of ps a of ps plus e to the I px u v of ps b dagger of ps, comma, and then here we have the daggered version. We have the daggered version. So if we dagger this, then we get e to the plus I p prime y. So we have p prime as integration variable and y as the argument of the field. And then we need to dagger it. So we get a dagger of p prime s prime times u dagger of p prime s prime. So u dagger is the daggered spinor, a dagger is the daggered operator. And then plus e to the minus I p prime y, b without dagger, and v dagger p prime s prime. That is the commutation. And now we have, of course, a with b, that gives 0. B dagger with a dagger, that gives also 0. But we also have something non-zero, a with a dagger, that is non-zero. And we have b dagger with b. And here b dagger and b comes in exactly this order. So no matter whether we have fermions or bosons, we always can apply the commutator in this order. So okay, and then we have all these integrals. And so dp tilde sum over s. And so should we go one more step, or do you want to do it at home? So one more step, okay. So one more step. So we have, first of all, now let's do a curly bracket. So we now put the commutator gives 4 terms. 4 terms because we have 2 times 2 terms. 2 out of the 4 terms give 0 and 2 other terms give non-zero. So let's consider the first non-zero term. the first non-zero term is the one, this commutator with that. So what is the result? So we have the two exponential functions, u and u dagger. These are just numbers, but here we have an operator a and a dagger. And the commutator of a with a dagger is written here, and it gives the usual thing with a delta function. So this commutator cancels exactly the p prime integral, and it cancels the sum over s prime. S prime becomes s, p prime becomes p. Okay, therefore we can write down the exponential function p and p prime, they are now equal. So we have e to the minus I p x minus y simply in the exponent. Then we have u dagger, and both have the argument ps. And that's it. That's it. That's the result of the first commutator. Or did I miss any factors? So next term, that with that. Okay. So b dagger with b, that gives something non-trivial, and it gives exactly the same. B dagger and b, they are already ordered in the way such that we can apply this commutator here without flipping signs or anything. So again, one integral is cancelled and the sum over s prime is cancelled. Afterwards, p and p prime, they are equal. So we get here the exponential function e to the I p x minus y from here and here. And then we have v dagger times with the argument p and s. That's it. And okay, and then you can apply the sum over s, e to the minus I p x minus y. So this sum u dagger with some argument p comma s, sum over s, is this completeness relation, and that gives just p slash plus m. That was what he wrote down the last time. This is a completeness relation that you can check, but here it's not u bar but u dagger, so we need to multiply from the right with gamma 0. And here again, the sum here over v bar gives p slash minus m. So here we have plus e to the plus I p x minus y times p slash minus m times gamma 0. So, and then you have to integrate. You have to remember that the time arguments x0 and y0, they are equal. That must be the case because the commutators are always required for equal time. And then this simplifies, so the time component with the energy P0 cancels, that doesn't contribute, and that is good because P0 is again this complicated abbreviation of the square root. So that would have a complicated dependence on the integration variable, but that cancels here in the exponent. So P0 doesn't appear. Here there is a P0 which appears. Here there is also a P0 which appears. And then we have P vector which appears here, P vector which appears here. P vector also appears in the exponent. And then you have two exponential functions. They differ only by the sign of P vector in the exponent. So you can actually relate these two terms by making an integral substitution, P vector going to minus P vector in one of the two terms. And then the exponentials become equal and something drops out here. And then after a few beautiful and very satisfying steps, you get delta 3 of x minus y. Okay. And I leave these very satisfying steps to you. So, but here one thing is important, so go through it yourself. But what is important for the structure of the Dirac theory versus Taylor field theory is really, again, here this different commutator, psi with psi dagger. In the Klein-Gordon case, we had psi and psi dot. That was the non-zero commutator. And here we have psi with psi dagger. And so in the spinor field, there appears here in these commutators those expressions here, p slash plus m, which come from those spinors, u of p and v of p. Those spinors play a role. They satisfy certain equations and they lead to such factors like p slash plus m or p slash minus m. In the Klein-Gordon case, there was no such factor. But instead, in Klein-Gordon, there was here phi dot, the time derivative. And so if you follow the steps, then at similar places, in the case of Klein-Gordon, there was no u dagger, but instead there was a time derivative which produced a factor proportional to p0 to the energy. That comes from the time derivative in Klein-Gordon. So if you really follow maybe side by side the Klein-Gordon calculation and this calculation, do it on 2 pages next to each other, then you will see here appears that, and in the other case there appears p0, and so for those reasons you get in the end similarly the three-dimensional delta function between x and y. But the intermediate steps are different. And so the psi dagger compensates kind of the appearance of those spinor wave functions.
ربما رأيتم المعلومة المهمة جدا جدا في هذا الفيديو، هو أن السبينر يقابل في الكلاين جوردن البينوت اللي هو الديريفيتيف بالنسبة للزمن. وهذا يؤكد على صحة كلامي أن السبين هو الذي يعطي الكتلة شكلها، وكأنما هذا الفرق بين الديريفيتيف اوف تايم والديريفيتيف اوف سبيس، هذا الفرق يعوض عن طريق السبينر بالنسبة لمعادلة ديراك أو بالنسبة للسبين نون زيرو اللي هو الفيرميون والبوزون سبين نون زيرو. وهذا يؤكد أيضا على ما ذهبت إليه أن الكتلة تحدد عن طريق السبين، وهذا شبيه طبعا بالثقب الأسود ومعادلة روي كير للثقب الأسود. وهذا التشابه غريب، هو ليس غريبا في نظريتي، هو تشابه عادي، لكن هذا التشابه يعني بين الفيرميونات وبين الثقب الأسود. وهذا يعني علينا نجد يعني النظرية التي توجد مثل هذا التشابه تسمى نظرية شاملة، تسمى نظرية كاملة. فالسبين هو الذي يقطع الكتلة، هو الذي يحدد شكل الكتلة، هو الذي يخبر الكتلة متى تتوقف من النمو. وأيضا الحركة في خط مستقيم تفعل ذلك، لكن يكمل عليها السبين. كلام جميل جدا.
And so of course the P0 has a certain behavior with respect to its signs. So in the Klein-Gordon case, when you have P0, then for example here in the green term you get plus P0, in the orange term you get minus P0. In the Dirac case, however, you get here in the green case you get UU bar, which gives P slash plus M, so plus P0. In the orange case you get VV dagger, that gives, where is it, P slash minus M, so again the same sign of P0. So the relative signs of the P0 terms, they are different in the Dirac case and in the Klein-Gordon case. And this is the technical reason why you need these different commutation relations in the two cases. And that then explains why we have Fermi statistics in one case and Bose statistics in the other case. So it comes down to such technical details of the calculation. Claim. claim is that we have a certain commutation relation of the Hamiltonian with a dagger of P and B of P. Namely, the commutator is plus P0 times a dagger of P comma S. And the interpretation is again that a dagger creates a particle or creates something, a wave mode, with energy P0. Plus P0, P0 is positive definite. So this a dagger creates a positive energy state. And the same is true for B. B dagger of P comma S also creates positive energy. And here again there is no plus minus, just to highlight this in order to avoid confusion. And so that means the Hamiltonian can be written as this object dp tilde. So there was a misprint in the Klein-Gordon case. It's dp tilde instead of d3p times p0 times the sum over s times a dagger a with some argument, however, minus b dagger. So up to a divergent irrelevant constant, this Hamiltonian is the same as the one we defined via Legendre transformation, and it satisfies the same commutation relation. So you can check first of all from the Legendre transformation that this is satisfied. Then you check that this satisfies the same commutation relations, and therefore the operators must be the same up to an irrelevant constant. And so here we have the wrong or an unusual sign, and we see that if we have fermions, then B dagger is minus B dagger B. So for fermions, this whole thing becomes plus B dagger B, and then it takes the usual form. However, for bosons, B dagger and B dagger B, they have the same sign, and therefore for bosons there will always remain this negative sign here in the Hamiltonian. Now, of course, we come to a very crucial point of the Dirac discussion, or maybe of quantum field theory in general. Namely, now we need to understand whether these particles are fermions or bosons. And let's first remember how we proceeded in the Klein-Gordon case, in the case with spin 0 in the scalar field. There we simply looked at all these relationships and we said, in a simple-minded way, okay, the relationships look identically to the normal harmonic oscillator relations, and therefore we immediately know what is our Hilbert space of states. We have this vacuum state, excited states, and they all have the usual properties, and I didn't comment much more on this except for saying this simple thing. And that was also correct. However, now it again looks very similar to the harmonic oscillator, but if you look closely, you see small differences, and you might wonder, hopefully, are these small differences simply to be ignored? Should we gloss over them and say again, okay, it's just as always? Or are these small differences maybe something to worry about? What are the small differences? One small difference is the sign here. And another small difference was the sign in the commutation relation for B and B dagger. B and B dagger had the wrong order. And so can we simply say that doesn't matter? Cannot be that important. We just rename B and B dagger, maybe then it has the right order. Or does it actually matter? Okay, and that is what we are now discussing. Choice of fermionic or bosonic statistics. And actually, let us begin with harmonic oscillators. Let us take a small break from quantum field theory and simply go back to ordinary harmonic oscillators to see what can happen. And before going there, let me even write down some fundamental requirements on any quantum theory. I stress here a physical quantum theory, which should be interpreted physically and which has the chance of actually describing nature. So two requirements, namely the Hamiltonian should be bounded from below. That means
طبعا يقصد بأن الهاملتونيان يكون bounded from below، يقصد به zero point energy والذي سببه الجاذبية. الجاذبية كما ذكرت أنه في حسب نظرية أنه ترفع الهاملتونيان تزيد الهاملتونيان، وبالتالي تكون أقل طاقة للهاملتونيان هي الطاقة التي تفرضها الجاذبية. طيب وماذا عن الطاقات العليا؟ هي الطاقات العليا الناتجة من الحرارة، سواء كان ناتج من اصطدام الذرات مع بعضها والجزيئات مع بعضها، سواء كان إذا كان هناك إشعاع، إذا كان هناك هذه الحرارة هي التي تسبب higher energies of Hamiltonian.
There are not arbitrarily negative energy eigenvalues. Why this requirement? Because otherwise there is no stable ground state. Otherwise there would be states of arbitrarily negative energy, and so by any small disturbance of your system you could bring the system in lower and lower energy states and gain infinite amounts of energy. That is unphysical, at least it's not observed.
طيب إذا وجدت هذا الهاملتونيان في فضاء، أو وجدت هذه الجزيئات في فضاء خالي تماما من الكتل، ما هو الباوندد أو الأوردر الحدود باوندري؟ ما هي باوندري؟ هو 10 أس ناقص 124 اللي هي في معادلة الطاقة. في معادلة الطاقة في نظريتي هي 10 أس ناقص 124. تعمل الجاذبية أو الكتلة M على رفع هذه القيمة المتدنية إلى أعلى. إذا فاتت القيمة الواحد فإن الفضاء الثنائي الأبعاد يدافع عن نفسه، إذا قل من قيمة واحد فإنه لا يدافع عن نفسه، ويعتبر الهاملتونيان هو هذه القيمة، أو تكون أقل قيمة للهاملتونيان يعتبر هذه القيمة بالنسبة للفضاء الثنائي الأبعاد. أما إذا كان غير موجود الكتلة فإن أدنى قيمة للهاملتونيان هو 10 أس ناقص 124. 10 أس ناقص 124، يعني قريب جدا من الزيرو. طبعا هي هذه القيمة تمثل ماذا؟ تمثل الماس جابا ولا انرجي جابا ولا معضلة الهيراركي في بالنسبة للانرجيز، حيث أن النسبية العامة تعطينا انرجي مختلفة عن الكوانتم ميكانيكس، والفرق بيناتهم 110 أس 120. نظريته تقول 10 أس 124، هذا هو الفرق بينهما. والنسبية العامة تخبرنا عن الجاذبية، والميكانيكا كم تخبرنا عن كتلة مطرودة من الجاذبية أو من فضاء التفاعل إلى فضاء أقل تفاعلا. هذا النظرة جعلت هذا الفرق الكبير في الطاقة، بحيث أننا لا نستطيع أن نعمل تراك لهذا الفرق في الطاقة حتى نستطيع أن نربط بين الجاذبية وبين ميكانيكا الكم. وهذا محير العلماء، لأنه هما على طرفي نقيض. الجاذبية تمثل طاقة مكثفة في وحدة الحجم، وميكانيكا الكم تمثل طاقة مطرودة من وحدة الحجم. هذا هو السبب.
So, and if you often have the possibility to add a constant to your Hamiltonian such that without loss of generality the lowest eigenvalue is simply 0. That is then a possible choice. But you can only do that if there is such that without loss of generality the lowest eigenvalue infinite amounts of energy. That is unphysical, at least it's not observed that this happens. So, and if you often have the possibility to add a constant to your Hamiltonian such that without loss of generality the lowest eigenvalue is simply 0. That is then a possible choice. But you can only do that if there exists an infimum of your eigenvalues. The second requirement, which is even more basic, and which you have never thought about maybe, is that the norm of states must be positive. So we always say quantum mechanics is described by a Hilbert space of states. Hilbert space contains as one of its axioms that all the norms of all states are positive. So that is an axiom of Hilbert space. So whenever you say Hilbert space, this is automatically implied. But actually it's a non-trivial physical requirement, because what would happen if you had a state with negative norm? Then you would not know how to interpret probabilities, because we say the norm of a state is the total probability of the state being observed. And if you have negative norms, then probability interpretation doesn't make sense. Let me actually add here norm of physical states, because maybe we need to relax this requirement a little bit and have unphysical states also. But at least for physical states which you can interpret experimentally, the norm must be positive. And that is now the problem. When I stressed many times that we need to construct a Hilbert space of states on which the operators are defined, then I had in mind that sometimes it is not possible to define operators which are defined actually on a Hilbert space where simultaneously both of these requirements are met. And that is what we will now see. Let us compare two types of simple harmonic oscillators. Case 1 is the normal one, namely you have some operator A and A dagger which satisfies A and A dagger commutator is 1. And let's do it fermionic or bosonic, plus or minus, but the result is +1. And we have some Hamiltonian H which satisfies H with A dagger, gives some omega A dagger where omega is positive. That is the totally normal situation of a harmonic oscillator. A dagger is the creation operator and it creates states with energy omega, and A dagger commute to 1. And you have bosonic harmonic oscillators, you also have fermionic harmonic oscillators, which you might have discussed in some lectures or not, but anyway, that is both okay. Case 2. A with A dagger plus or minus is now -1, but H with A dagger is still omega A dagger with omega bigger than 0. Okay, so we flip the sign in one of them. What happens? And let me just say, maybe in a different color, there would of course in total be 4 obvious cases. plus, 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 minus, minus, plus, minus, minus, and so on. So let's briefly think about the other cases. So for example, you could have here A with A dagger plus minus equal minus 1. And here we could have minus omega times A dagger. So that would be a third case. If you encounter that third case, what do? You would now swap the notation A and A dagger. Simply swap the notation. If you swap the notation of A and A dagger, then you have here A dagger A gives minus 1. And then you need to distinguish. If we are in the bosonic case and we swap A with A dagger, then we get A dagger A minus is minus 1. So A with A dagger gives plus 1. And here, if you swap A with A dagger, then you have here A decreases the energy and A dagger again increases the energy. So that is then the normal case, case 1. So for the bosonic case, this third case is equal to the first case. Just you have accidentally chosen unusual names for your operators, that's all. But for the fermionic case, if you swap A with A dagger, then you keep the minus sign here because it's plus. So you keep the minus sign. But here again, you convert the minus sign into a plus, so you go to case 2. But anyway, the third case is not independent. You can trace it back to either case 1 or case 2. And similarly, if you have here plus 1 and here minus omega A dagger, then the opposite happens. So you swap A and A dagger, and then the bosonic case becomes case 2, and the fermionic case becomes case 1. So simply, that means we only need to consider those two cases in white, where we always say that A dagger is the state that creates energy, but A with A dagger, they either commute to plus 1 or to minus 1. That is the only thing we need to consider. And now let us consider it and check whether we can define those operators on a Hilbert space which satisfies both properties. So for both cases, case 1 and 2, we now do essentially what I assume you must have done in ordinary quantum mechanics lectures when you discuss the Hamiltonian, because there you must go through the identical procedure. So we assume that there exists at least one energy eigenstate, let's call it E, which is not a null vector, and which is an energy eigenstate H E gives E times E. We assume that one energy eigenstate exists, and we also assume now that one of our two requirements is satisfied. Namely, what do we assume? We assume that the Hamiltonian is bounded from below. All H eigenvalues are bigger or equal than some number, let's call it Eg for ground state energy, and that must be bigger than minus infinity, so it's an actual number. Okay, so that is our starting assumption. Then what did you do in quantum mechanics? You start with this energy eigenstate and you hit on it with the annihilation operator, A on E. That gives you some result. And if you construct your operators on the Hilbert space, then that result must be an element of your Hilbert space of states. So this is some well-defined state, E prime. What is the property of E prime? If you hit on E prime with the Hamiltonian, then from the commutation relations you know that A decreases the energy by the amount minus omega, and therefore this is an energy eigenstate with the eigenvalue E minus omega So you get this equation, an eigenvalue equation. This is an automatic consequence of the commutation relation on the right with the Hamiltonian. And actually here there are two possibilities. It can be that the state E prime is a non-null state, an actual state with some norm, or it could be the null vector, could be. But then the equation is also satisfied. Either way, for sure we know that this equation is valid and we know that this object here exists. But now you can repeat this procedure as many times as you want. You can hit on, so you know E prime again satisfies the same assumption. And so you hit again with A and you decrease the energy by omega more and more times. So you can decrease the energy by as many numbers of omega as you want, unless at some point the state becomes the zero vector. And so if the state never becomes the zero vector, then you get a contradiction, because then you get energy eigenvalues with arbitrarily low negative eigenvalues, and that is a contradiction to the boundedness of the Hamiltonian. So therefore it follows that there exists some number n0, element n, such that A to the n0 times the state E gives the null vector in your Hilbert space, whereas A to the n minus 1 still gives you a non-vanishing state. There must be such an integer which has this property. So n is the first which annihilates the state, and n0 minus 1 doesn't yet annihilate your state. Such an n must exist. And then we have, of course, defined in this way a certain state, A to the n0 minus 1 acting on E. That is a special state. Let's call it 0, like the vacuum state, because that is the state which is annihilated by one additional application of A. Just to highlight, this is not necessarily normalized, but we definitely know it's a non-zero state. So we get a special state, 0. This might be the ground state, but it's actually not guaranteed that this is the overall ground state, because in general there might be other operators which also can be minimized and so on. But it is one special state which has this property, and now we can write down the H on this vacuum state is an energy eigenvalue, because it was constructed like that, and let's call the energy eigenvalue E0, and we know A on this state is the null vector in our space. This is what we know about this state. And the state itself is non-zero. So then we can define excited states by acting with A dagger. We don't care about normalization here, just to be clear. They are not normalized states, but we can simply define states n by A dagger to the power n acting on the vacuum state. We can do that for all n. And we know that they are energy eigenstates with the eigenvalue E0 plus n times omega acting on n. And now comes the crucial point, namely we can finally ask what is the norm of those states. And the beautiful thing about quantum mechanics is that the norm is calculable. We can calculate what the norm is. It's not something that you can decide about. The operator commutation relations fix the norm. And that is what we now see. And we only need to look at the first excited state, 1. And we simply take this scalar product 1 with itself. And if the theory is reasonable, that must be positive. But let's see what comes out. So the state 1 is defined by acting on the vacuum with A. So we get here a dagger A. That is our thing that we need to calculate. And now we can use our commutation relations, and that is the point. So A and A dagger. So okay, I deleted how the commutation relations look like, but depending on fermions or bosons, this is plus or minus A dagger A, the opposite order, plus for bosons, minus for fermions, and then we have plus minus 1, depending on whether we have this case 1 or case 2. Now, so yeah, let's replace this by that. Then we have, first of all, let's do it case by case. Case 1. Case 1 has the plus 1. What happens to this when we insert A dagger A into the vacuum? What do we get? Yes, we get 0 because A hits the vacuum, and so that gives 0. And so the only thing that remains is the plus minus 1. So therefore, in case 1, the norm of our state 1, 1 is the same as the norm of our 0 state. It's equal 1, 1 equal 0, 0. But in case 2, we have here minus 1, and therefore our norm state 1, 1 is equal to minus the norm of the state 0, 0. And so that shows you now that our Hilbert space of states is not a Hilbert space in the second case. It's a vector space with a scalar product which is not positive definite because it contains one state, so we don't know what is this. But anyway, it cannot be that both states have positive norm. One of them must be negative, or both must be 0. But either way, this contradicts our Hilbert space postulate that all states which are not a null vector have positive norm. So that is a contradiction to Hilbert space axioms. And then just to conclude, that is what you have done in the harmonic oscillator, I assume, because now you, in the harmonic oscillator, you only have this situation, and then you would say, okay, that means that our states n here all have positive norm, and you can now define your Hilbert space by saying that this is the basis of your Hilbert space of states. Then you know on these states perfectly well how A acts, how A dagger acts, how the Hamiltonian acts. And therefore you have completely constructed an infinite dimensional Hilbert space with a basis, and all the operators have a completely known behavior. And the operators satisfy the commutation relations which you have required. Then you have fully constructed your theory, and the theory is consistent. So that is case 1. Can construct the basis of states with positive norm. All requirements are met. But in case 2, this is just not the case. In case 2, we did it in the way that we started from assuming that our postulate on the boundedness of the Hamiltonian is verified, and then we conclude that the states are not positive definite. You could do it in the opposite way, assume that the states are positive definite, then you will discover that the Hamiltonian is not bounded from below. So it goes in both directions, but anyway, here I say there are states with negative norm. That is a contradiction to our Hilbert space postulate, and it means we have not a consistent quantum theory. And that shows you that actually these commutation relations are quite powerful and tell you these things about the construction of your theory. And so it's maybe the lesson for you, which you might not have thought about before, is that not all commutation relations can actually be satisfied on a reasonable Hilbert space of states. That is the general picture, and now we can apply this understanding to our Dirac case. So in our Dirac case, we have the following. A with a dagger, let's ignore the arguments, was some factor n, which is positive, and h with a dagger, that was p0 times a dagger, where this p0 is also positive. So that means the a's, they always behave like this consistent case 1. So for the a's, everything is okay. And that was true both for fermionic and bosonic relationships. But in the B case, we have this B dagger B plus or minus is equal to n, where n is positive, and h B dagger is p0 times B dagger with positive p0. So and here we had the wrong order, and therefore now this is one of these orange cases. So for bosons we get here the wrong sign. For bosons we get the wrong sign because then we get here a minus. So we have here a minus, and that means we would be in our case 2. But for fermions there is no problem. For fermions we can flip the order. B dagger B, B dagger has the same anti-commutator, and therefore we are in our case 1. Case 1 only for fermions. So let's summarize this whole thing. We first of all spin 1/2 particles must be fermionic. And this whole thing is an example of a more general theorem, which is called spin statistics theorem. Which is a fundamental quantum field theory, relativistic quantum field theory theorem, which always tells you that integers n requires bosonic statistics, whereas half integer spin requires fermionic statistics. And we have seen here the example of the Dirac case, which describes spin 1/2 particles, and we see that statistics must indeed be fermionic. And in the previous case, scalar field had to be bosonic. And what is really kind of neat is that here we have something, fundamental physical prediction, namely this relationship, which is a prediction that has macroscopic impact. Because whether a particle type is bosonic or fermions has macroscopic impact. You know, light waves are bosonic, and so they can coherently add up to macroscopic electromagnetic fields. Whereas electrons are fermions, and so they satisfy the Pauli exclusion principle. They build up stable atoms and molecules, but you do not see macroscopic coherent electron fields. And so this is a macroscopic property that you can see in daily life in non-relativistic contexts, but the reason comes from relativistic quantum field theory, so from absolutely microscopic and relativistic physics. All right. Any questions to this? So this is one of the important fundamental quantum field theory results. And of course, what we have now seen is just an example. But you see where it comes from these different types of commutation relations between creation and annihilation operators. Now we have a few more minutes, and we can start maybe with a new section, unless you have more questions to this topic here. The new section deals with a question that has now already come up, because I mentioned that these particles here have spin 1/2. But have we already shown that? No, we have not yet shown that. We only know that we started with the 1/2, 0 representation of the Lorentz group to define our field operator. But we do not yet know what the particles actually do. And you remember this mismatch between the representations of fields and the representations on the level of particle states. And so we should now really investigate what are the Lorentz transformation properties of those particle states created by our new A and B Decker operators. In particular, we should then again go to the rest frame and check what is the angular momentum of those particles at rest to see what is their spin. And for that, we of course need to construct the angular momentum operator. And that is our next step. We did the same thing for the Klein-Gordon field as well. And we did it using the Noether theorem, which gives us a precise recipe to construct all the Poincaré group generators. And so we will do that here. And then once we have them, we can apply them and verify that the particles have, of course, spin 1/2, which is not a surprise, I guess, but we should really go through the details to check this. So P mu and J mu nu. So we need to look at the Poincaré transformations. First of the classical field psi. And then we use the Noether theorem to construct operators and conserved quantities which are conserved because of Poincaré invariance, and they will be interpreted as momentum operators and angular momentum and boost operators. So the Poincaré transformation is again x goes to lambda x plus a, which is approximately equal to x plus omega x plus epsilon, and our field psi goes under lambda a to a new field psi prime, which has the property psi prime at lambda x plus a is equal to s of lambda times psi of x, and s of lambda was the Dirac representation of the Lorentz group given by I/4 commutator of gamma matrices. So and we can then write it in infinitesimal form. Psi prime at x is given by s of lambda psi of x minus omega x minus epsilon, and this s of lambda is given by the unit matrix in 4 dimensions minus I/2 times omega rho sigma times s rho sigma times psi of x minus omega x minus epsilon, where the s rho sigma is given by I/4 commutator of gamma rho times gamma sigma. Okay. This is all our definition of the Poincaré transformation. And now we did this in general in the exercise actually yesterday. And so let me just use the result of the exercise, which had this general form. So we can say that psi prime at x is given by psi at x minus epsilon mu d mu psi at x, and then minus I/2 omega rho sigma, and then we have this combination S rho sigma plus L rho sigma acting on psi at x, where L rho sigma corresponds to angular momentum and is x rho d sigma minus x sigma d rho. So then we have a very beautiful form of our field transformation given in terms of those operators, and we know that we now can write our Noether currents in the following way, namely, let me directly jump to the result, because that is the same as for the exercise and also the same as for Klein-Gordon, except for the additional appearance of the S rho sigma, which we discussed yesterday in the exercise. And so then the conserved relationship looks like this. 0 is equal to d rho of psi bar I gamma rho minus epsilon mu d mu psi minus I over 2 omega, let's say, mu nu S mu nu plus L mu nu acting on psi. So this is one bracket here, plus epsilon rho times L plus omega rho sigma x sigma times L. So this is our conservation law, and that is the same as yesterday in the exercise. And now we can read off coefficients in front of epsilon and in front of omega to obtain concrete conserved currents which either correspond to translational invariance or to Lorentz invariance. And so that, and then this will be the last thing we do. Let's read off the coefficient in front of minus epsilon mu. That gives us the current for translational invariance P rho mu, and I will just copy it from here. Psi bar I gamma rho d mu psi minus G rho mu times L. And that would be a definition of our energy momentum tensor, and the zero component of this integrated over x gives us the momentum operator. Then similarly, we can obtain the coefficient of 1/2 omega mu nu. That gives us a current m rho mu nu is equal to psi bar gamma rho S mu nu plus L mu nu psi plus G rho mu x mu minus G rho mu x mu times L. And so this is literally copied from our exercise yesterday, but of course you can derive it once again in the same way as we did it yesterday by going through the standard steps and simply expanding the field and plugging into the Noether formula, and then we obtain these results. And so here we will stop today, but clearly here we have two expressions which will be the basis of our momentum operator and our angular momentum and boost operator the next time. If we go to the quantum theory, the fields are replaced by operators, and then we have well-defined commutation relations of all these objects, and we can check that the Poincaré representation is satisfied and so on, and then we can apply them onto states and obtain the desired result. Okay.
طيب تعالوا نقف هنا قليلا. في معادلة كلاين جوردن عرفنا أن هذه المعادلات تكافئ النسبية العامة ولكنها على طرفي نقيض، تعتبر طاقة مطرودة من التفاعل لكنها لها نفس الاستراكشر بالنسبة للنسبية العامة لمعادلة أينشتاين. هنا الوضع مختلف. أولا تعالى المعادلة الأولى نجد أن الاشتقاق لصاي واحدة، الصاي الثانية ليس فيها اشتقاق، في حين أنه معادلة كلاين جوردن الاشتقاق فيهم الاثنين. الشيء الثاني نجد أن الجي رو ميو اختلفت، هناك جي رو ميو في البسط، هنا جي رو ميو في المقام. أقصد في رو ميو رو فوق سبسكريبت أو السوبر سكريبت وميو سبسكريبت، وهذا يعني ربما يكون له دلالته. في كلاين جوردن نجد جي روميو الاثنان سوبر سكريبت، الاثنان في فوق، هنا واحدة فوق وواحدة تحت. والأجراء انت تمثل السكيلر السكيلر ريتشي. نجد هنا في تي أيضا، التي أيضا واحدة فوق واحدة تحت، حتى التي واحدة فوق وواحدة تحت. ماذا يعني هذا؟ ماذا يعني فوق تحت؟ فوق عرفناها، يعني نقول أنه أنا على ما أظن أنه طبعا فوق يعني الاثنان كونترافاريانت، مثلا فوق تحت واحدة كونترافاريانت واحدة فاريانت، كأنه هناك نوع من الاختصار تعمل هنا. في معادلة كلاين جوردن لا يوجد اختصار، الاثنان فوق، هنا واحدة فوق واحدة تحت، كأنما عمل نوع من الاختصار. أنا في الحقيقة لست بارعا في معرفة هذه الأمور لأنها لم تمر عليها كتحدي. اليوم مرت علي فيجب أن نضع لها اعتبارا وأحاول أن أحللها، لكن هذا هو الاختلاف. نلاحظ أن الكيو اي دي أولا نلاحظ أن معادلة ديراك تعتبر حل معادلة كلاين جوردن، ده واحد. اثنين أن معادلة كلاين جوردن تحتوي على بوزونات، والكيو اي دي تحتوي على بوزونات، بوزون دبليو زي وبوزون دبليو، والكيو اي دي ذات نفسها تعتبر الوجه الثاني للنسبية العامة، وكما ذكرت على طرفي نقيض لكن لها نفس الاستراكشر للنسبية العامة غير أنها مطرودة من التفاعل. فبالتالي وكأنما الشيء الذي نريد أن نلاحظه أيضا أن معادلة ديراك تعتمد على المكان فقط، وكأنما هذا الكونتراكشن اللي حصل بين البسط أو من فوق والتحت هو كأنما سببه حذف الزمن. إذا حذفنا محور الزمن سنضرب في جي ميو معينة، جي ميو نيو معينة، يعني جي رو ميو مثلا أو نيو، يعطينا هذا كونتراكشن وحذفنا فيها الزمن، كأنما هذه المعادلة تخبرنا أنه تم حذف الزمن بهذه الآلية، يعني عمل نوع من الكونتراكشن، تحول شيء ما تحول إلى سكيلر، شيء ما انتهى من شيء آخر، أو قمعنا شيء آخر degrees of freedom، قمعناها عن طريق هذا الكونتراكشن، وأعتقد أننا قمعنا تغير الزمن لكي يعطينا الكتلة. أعتقد هذا أنه حذفنا شيء ما مهم جدا في موضوع الكتلة، وأجبرنا معادلة ديراك أنها تعتمد فقط على المكان وليس على الزمن، وهذا كأنما عملنا كونتراكشن لشيء ما. يعني مثلا في تلك المعادلة كلاي جوردن نجد أن رو ميو موجودة في البسط، وهنا رو ميو موجودة في المقام، وكأنما ضربنا في جي ميو في البسط وميو في المقام. شيء غريب يعني. هل يمكن يكون هناك جي مثل هذا، أو مثلا جي ميو نيو، بحيث أنه الميو في المقام، الميو الميو في البسط والنيو في المقام مثلا، وبالتالي جعلنا جيرو المفترض تكون جيرو نيو، لكن حتى يعني بسبب أننا أول محاضر لم يجري للمقارنة جعلها جيرو ميو ومفترض تكون رو سيجما مثلا. بالتالي احنا ضربنا في أمر معين، ضربنا في نعم ضربنا في مثلا ضربنا في جي اللي هو متريك تنسر سبسكريبت رو مثلا سيجما ميو. بالنسبة لمعادلة كلاين جوردن ضربنا جي سبسكريبت سيجما ميو، فعملنا كونتراكشن بين الميو التي في الأعلى والميو التي في الأسفل، وتركت السيجما التي هنا تساوي الميو. ولاحظ أنه الميو ماذا تعني؟ من المفترض الميو تعني شيء غير الفضاء رباعي الأبعاد، يعني ربما تعني السبين. رو معروفة هو الدنسيتي، كرنت دنسيتي والتشارج دنسيتي، هذا معروف الرو. لكن الميو هنا شيء آخر غير الفضاء رباعي الأبعاد، يعني شيئا آخر غير طبعا احنا نتكلم عن continuity او معادلة الاستمرارية. فالرو يعتبر التشارج density، والبيو في معادلة كلاين جوردن يعتبر الفيكتور التشارج فيكتور اللي هو حركة التشارج في الفضاء رباعي الأبعاد أو ثلاثي الأبعاد، وبالتالي تكون الدنسيتي ناقص الفيكتور يساوي زيرو. هنا كأنما عملنا ماذا؟ حولنا الاندكسز، بدلا من كان بدلا بعد ما كانت معادلة استمرارية في حركة خط مستقيم أو حركة أفقية أو حركة نقول في الفضاء ثلاثي الأبعاد عن طريق مومنتوم اللي هي معادلة استمرارية عن طريق المومنتوم، وهي معادلة أينشتاين. طبعا هنا بدلنا الحركة المومنتوم إلى الأنجولار مومنتوم. نعم هذا صحيح، هذا هو الإجابة، هذه هي الإجابة. أننا في هذه المعادلة تركنا المعادلة الاستمرارية التي تتحدث عن الفرق بين التشارج دنسيتي والفيكتور دنسيتي أو حركة التشارج في الفضاء رباعي الأبعاد أو ثلاثي الأبعاد. هنا عملناه سبين. طيب بما أننا عملناه سبين، فهنا النسبية الخاصة لا، النسبية العامة لا تعمل، أو على الأقل لا تعمل في حالة مستوى الجزيء أو مستوى الإلكترون مثلا أو مستوى الفيرميون ككل، لأنه نحن نتحدث عن معادلة استمرارية من حركة في فضاء رباعي الأبعاد من هنا لهنا. هنا أنت عملت سبين، يعني عملت حركة دورانية في مكانك وأنت ثابت. فشيء غريب جدا، يعني شيء غريب جدا. لهذا نجد أن الاشتقاق أجرت في صاي واحدة وليس في الدبل صاي. هناك في كلاين جوردن عملنا اشتقاق في دي ميو دي ميو بالنسبة لصاي ودي نيو بالنسبة لصاي، هكذا. هنا لا، هنا صاي بار مضروبة في دي ميو صاي. لا نحتاج إلى الاشتقاق في الفضاء رباعي الأبعاد، لا نحتاج إلى معادلة كلاين جوردن، لا نحتاج إلى الادنتيكال المتطابقة إنه دي ميو كوفاريانت كونترا فاريانت تعطينا مشتقة بالنسبة للزمن تربيع ناقص المشتقة بالنسبة للمكان تربيع، أو معادلة الحركة، معادلة الموجة المعروفة. هنا نتحدث عن السبين، لا نحتاج لذلك. السبين يعني جسيم في مكانه وهو يدر. لكن هل ليس هناك تيار؟ هناك تيار يذهب، هناك تيار يتحرك في هذا الأمر تبع الدوران. لكن هنا الفضاء أقل، هنا الفضاء أقل، هناك فضاء أكبر يتحرك الشحنة تتحرك في فضاء أكبر، هنا تتحرك في فضاء أقل. يعني النسبية العامة يمكن تطبيقها لكن في فضاء أقل، اللي هو فضاء حدود سطح الإلكترون أو سطح الفرميون أو شيء كهذا، يعني شيء كهذا. المعادلة الثانية طبعا السبب الذي جعل هذا التغير الذي يحصل في المعادلة الأولى ظهر مباشرة في المعادلة الثانية، لأن المعادلة الثانية تم إضافة الاس نيو، هذا الحد غير موجودة في معادلة كلاين جوردن. ومعادلة كلاين جوردن تعتبر سبين زيرو، وهذه معادلة هي سبين 1 وسبين هاف، الاثنين مع بعض، سبين 1 وسبين هاف. بالتالي السبين أوجد شيئا آخر اللي هو أدخل الاس بسبب هذا، بسبب الكونتراكشن الذي عملناه، أدخل معادلة الاس، وأدخل أيضا جاما رو. هناك ليس في جاما رو، هناك في مشتقة بالنسبة للصاي. هنا أصبح الصاي بار مضروبة في جاما رو، هناك مشتقة بالنسبة لصاي اللي هو مشتقة رو دي رو بالنسبة لصاي. هنا دخلت الاس ودخلت ال بعد ذلك المعادلة الثانية كما هي، المعادلة الثانية ولا الحد الثاني كما هو، بس فقط أيضا حصل كونتراكشن بين الرو والميو، لكن الاكس ميو والاكس نيو كما هو والأجرام كما هو. لكن هنا في الحد الأول أدخل الاس والال، هناك ليس هناك اس وال، وإنما هناك أيضا عدد متغيرات مضروبة في بعض. كيف تعال نشوف ماذا يوجد هنا. انظر هذا ما يوجد. أول شيء نجد الام دالة في 3 متغيرات. هنا وجدنا الام، هنا وجدنا الام، يعني أيضا دالة في 3 متغيرات مع وجود التحويلات اللي هو الكوفارينت والكونترا فاريانت. طيب تعال هنا ثاني نجد أن دي رو فاي، وهناك فاي بار مضروب في جاما رو. هنا انظر إلى هذا الأمر، اكس ميو دي ميو ناقص اكس نيو دي ميو. هناك تم استبدالها بإس زائد اس مضروبة في ال يعتبر ما ذكرناه سابقا، لكن الاس يعتبر شيء مختلف. نعم الاس يعتبر شيء مختلف. لكن ال هو نفسه الفات اللي هو دي ميو. ال عبارة عن اكس ميو دي ميو ناقص اكس ميو دي ميو. فظهر شيء آخر يسمى الاس. هنا ظهر شيء آخر يسمى الاس. ظهرت هذا الاس اس ميو نيو بسبب هذا الكونتراكشن. لماذا حل الاس؟ لأنه الاس كما قلنا تحدد الكتلة. فاتنازلنا عن أحد الأبعاد بالنسبة للفضاء، لأن الرو دينسيتي الرو كما هي موجودة في السوبر سكريبت، لكن في السوبر سكريبت الآخر بفترض تكون ميو نيو. هنا تنازلنا عنها وضربناها في جي ميو نيو كوفاريانت كونترافاريانت، لا كوفاريانت على ما أعتقد. وبالتالي أعطانا ماذا؟ أضاف لنا قيمة أخرى أو متغير آخر اسمه الاس. والاس هو ما هو الاس؟ هو طبعا هو السبين. والسبين دخل في هذه المعادلة بسبب هذا الكونتراكشن وحل محله. وبالتالي هذا الإحلال لا هو ليس حل محله، لكن هو يضيف زيادة، يضيف هذا الحد. هذه الإضافة جعلت أن الإس يمكن أن تعطينا معلومات عن الكتلة. وأعتقد أنه هذه المعلومات عن الكتلة أنها الإس تستطيع تحديد شكل الكتلة مرة أخرى. الإس تستطيع تحديد شكل الكتلة مرة أخرى، يعني من عن طريق هذه المعادلة. طبعا الفيديو القادم هو تكمل لهذه المعادلة وسنرى ذلك، لكن نجد أن الإس هنا يحدد لنا شكل الكتلة، يحدد لنا شكل الكتلة، لأنه يمكن أن يكون مكافئا ل ميو نيو. وأعتقد أنه هنا يكون في غوص يكون هو نسى هذا الغوص، لأنه كله يكون مضروب في صاي. الاس زائد ال مضروب في صاي، مفترض كده. إذا حدث ذلك أن الاس زائد ال مضروبة في صاي كلها مع بعض، هنا يعطينا ماذا؟ هنا يعطينا أن الاس تكون مكافئة لل الاس تكون مكافئة لل، وهذا يعطينا بدورها أن هذا الحد اللي هو اكس ميو في دي ميو ناقص اكس ميو دي ميو، هذا الحد له علاقة، يكون له علاقة بالكتلة مثلا، يكون له علاقة بالكتلة، لأنه هو يعبر عن الترانسليشن موشن. والحد الثاني هو يتعلق بال على ما أعتقد يتعلق بالبوست. الحد الثاني يتعلق بالبوست على ما أعتقد، لأنه فيه رو. نعم، هنا ما في رو، هنا في ميو نيو، وهذا يتعلق بالترانسليشن موشن. والحد الثاني فيه رو، نعم، تتعلق بالبوست. أعتقد ذلك. نحتاج إلى مزيد من المراجعة. هذا الأمر يحتاج إلى مزيد من المراجعة، لكن أنا ما أريد أن أوصله هنا أنه الإس هناك يمكن أن تعطينا شيئا معلومات عن تأثيرها على الكتلة. سنشوف هذا في الفيديو القادم إن شاء الله بإذن الله. السلام عليكم ورحمة الله.